What if SpaceX's Dragon could beat China to the moon? While NASA burns $5.2 billion per Artemis launch, experts reveal Dragon's 9.5-ton design crushes Orion's bloated 26.5 tons. Dr. Zubrin dropped a bombshell. Dragon could reach lunar orbit using Falcon Heavy, slash costs by 90%, and launch monthly instead of yearly. But here's the catch. It needs modifications NASA never saw coming. As China races ahead, could Musk's Dragon Gambit be America's secret weapon? Let's dive right in. Here's what nobody wants to admit. NASA's Artemis program is bleeding money faster than a punctured fuel tank. Every single launch costs American taxpayers $5.2 billion. That's not a typo. That's the price tag for getting 4 astronauts to lunar orbit and back. Meanwhile, China's Chang'e missions are advancing methodically, and their next crewed lunar mission could happen sooner than anyone expects. But what if there's a backdoor solution hiding in plain sight? Let's talk cold, hard physics. SpaceX's Crew Dragon weighs 9.5 tons. NASA's Orion? A whopping 26.5 tons. That's nearly 3 times the mass for essentially the same job. Dr. Robert Zubrin, founder of the Mars Society, put it bluntly. Dragon isn't just cheaper than Orion. It's vastly superior because it's vastly lighter. This isn't just about weight, it's about efficiency. Every kilogram matters when you're hauling mass 240,000 miles to the moon. While Orion struggles under conflicting NASA requirements from multiple administrations, Dragon was built with one clear purpose: get humans to space efficiently. Here's the engineering brilliance. Dragon has 50% more internal space than the Apollo capsule, while weighing only 20% more. That's smart design beating bureaucratic bloat. So how do you actually get Dragon to the moon without building entirely new rockets? This is where SpaceX's existing hardware becomes the game changer. Falcon Heavy already exists and launches payloads regularly. The solution is elegantly simple. First, Dragon launches with crew on a standard Falcon 9 rocket to low Earth orbit. Separately, a Falcon Heavy launches, carrying a fully fueled upper stage. These two vehicles rendezvous in orbit, where the Falcon Heavy upper stage becomes Dragon's lunar taxi. This upper stage handles everything: trans-lunar injection to get to the moon, lunar orbit capture, and the trans-Earth injection burn for the return journey. It's like having a dedicated space tug for lunar missions, using hardware that already exists. The critical question: can Dragon actually survive a lunar mission? The flight to the moon and back takes at least 6 days, pushing Dragon beyond its typical International Space Station missions. Dr. Zubrin calculated the life support requirements with precision. One crew member consumes roughly 1 kilogram of oxygen per day. For 2 astronauts over 10 days, that's 20 kilograms of oxygen stored as compressed gas at 3,000 psi, requiring just 0.075 cubic meters of storage space. Dragon's internal volume is 9.3 cubic meters. We're talking about less than 1% of available space for extra oxygen tanks. The math works beautifully, proving Dragon has the life support capacity for extended lunar missions. Here's where the plan gets even more interesting. Instead of waiting for the complex Artemis architecture, consider this approach. Dragon carries crew to low Earth orbit, then transfers them to a Starship human landing system that serves as a space tug between Earth and lunar orbit. Once at the moon, astronauts ride Starship directly to the lunar surface, completely bypassing the complicated near-rectilinear halo orbit requirements that slow down Artemis missions. For the return journey, a modified Dragon launched earlier by Falcon Heavy waits in lunar orbit. Since this return vehicle launches uncrewed, it doesn't need human rating certification for Falcon Heavy. The crew transfers from Starship to Dragon for the familiar ride home and proven hardware. Let's address the real technical hurdles honestly. Sending Dragon beyond Earth orbit requires substantial modifications that can't be ignored. The communication system currently relies on GPS, completely useless beyond Earth orbit. Dragon needs a complete deep space communication and navigation system overhaul. Radiation protection presents another significant challenge. While protecting astronauts is achievable, hardening all electronics against cosmic radiation and solar flares requires extensive work. Most critically, the heat shield faces a major test. Returning from the moon means hitting Earth's atmosphere at 11 kilometers per second, much faster than low Earth orbit re-entry speeds. Dragon's current Pika X heat shield likely needs upgrades or complete replacement to handle these lunar return velocities. Here's the constraint that could derail everything: Dragon's independent operation time. According to NASA documentation, Dragon can operate independently for approximately 5 days with a 4-person crew. Some estimates extend this to 7 to 10 days maximum. Compare this to Apollo's 14-day rating or Orion's 21-day capability. Most Apollo lunar missions lasted 8 to 12.5 days. Dragon technically fits this range, but with zero margin for error. Any delays or complications could spell disaster. The solution requires enhanced life support systems, expanded consumable storage, and possibly docking capability with lunar infrastructure like the Lunar Gateway. Each addition means more weight, complexity, and engineering challenges. While America debates Dragon modifications, China continues systematic advancement. Their Chang'e program has methodically achieved every milestone: lunar orbit, landing, sample return, and far-side operations. Crewed lunar missions represent their logical next step. China's approach differs fundamentally from both NASA's Artemis and SpaceX's concepts. They build methodically, test thoroughly, and advance without the political pressures that reset American space programs with each administration change. The question becomes urgent. Could Dragon missions beat China to establishing permanent lunar presence? The answer depends on moving from debate to development. This matters beyond national prestige. It's about transforming space economics. Dragon lunar missions could cost hundreds of millions instead of $5.2 billion per Artemis launch. That's not just savings. It's the difference between occasional lunar visits and routine operations. Consider the possibilities: monthly Dragon missions to the moon, rotating crews, extended research programs, rapid technology testing. At Artemis prices, we get 4 total missions. At Dragon prices, dozens of missions become possible within the same budget. Dragon missions could accelerate lunar infrastructure development faster than any alternative approach. Each mission delivers essential equipment, supplies, and personnel for permanent lunar facilities. Those 1,000 Starship landings needed for a lunar city become economically viable when crew transportation costs drop by 90%. Dragon doesn't just reach the moon, it makes staying there affordable and sustainable. NASA leadership understands Artemis costs are unsustainable. Congress recognizes this too. The question isn't whether alternatives will be considered, it's when. Dragon lunar missions offer a politically acceptable solution, leveraging existing American commercial capabilities while dramatically reducing government costs. SpaceX already transports American astronauts to orbit, launches national security payloads, and provides global communications. Extending this partnership to lunar missions isn't radical, it's logical evolution of proven capabilities. Dr. Zubrin calls his Dragon lunar concept Artemis 8, essentially replicating Apollo 8's historic lunar orbit mission with modern, efficient hardware. This isn't science fiction waiting for breakthrough technologies. It's engineering reality waiting for implementation decisions. The technical feasibility is clear. Dragon can reach the moon. The physics work, the engineering challenges are solvable, and the cost benefits are undeniable. Success depends on political will, technical execution, and whether China forces America's hand by reaching the moon first. The choice facing America is stark: continue funding the bureaucratic approach or embrace the efficient path. With China advancing steadily toward their lunar goals, this decision becomes more critical every day. This is exactly why Dragon's lunar plan changes everything. While NASA burns $5.2 billion per Artemis mission, Dragon could slash costs by 90% and beat China to establishing permanent lunar presence. What this means is clear. The moon race isn't about who gets there first anymore. It's about who can stay there affordably. Dragon's 9.5-ton efficiency versus Orion's 26.5-ton bloat proves that smart engineering beats bureaucratic spending every time. We're looking at monthly lunar missions instead of yearly spectacles. That's not just progress. That's revolution. The next 18 months are critical. SpaceX's Starship tests, NASA's budget decisions, and China's lunar timeline will determine if this becomes reality. Dragon lunar missions could launch as early as 2026, if development accelerates? Will Dragon lunar missions force NASA to abandon Artemis? Could this spark a new space race with monthly moon flights? Drop your predictions in the comments below. This is Space Hub, your source for space news that actually matters. Hit that like button if this analysis opened your eyes to Dragon's potential. Subscribe and ring the notification bell so you never miss our deep dives into the space stories shaping our future. Share this video with anyone who thinks space exploration is too expensive to sustain. The moon isn't the destination, it's the stepping stone. And Dragon might just make that journey routine. SpaceX's S-38 static fire test failed spectacularly on September 18th, and the reason why could derail everything. No fuel reached the tanks, no frost formation, no ignition, just dead fuel lines and a ground system that completely collapsed when it mattered most. Engineers immediately suspected pump failures and fuel line malfunctions after months of intensive booster testing. The brutal timing, S-38 is the final V2 Starship before the V3 revolution begins. This isn't just a delay, it's exposing critical weaknesses in SpaceX's infrastructure. The same ground systems that powered their record-breaking pace may now be the bottleneck destroying their momentum. Let's dive right in. At exactly 6:47 a.m. Central Time, SpaceX's tank farm came alive with activity. Massive venting clouds signaled the beginning of what should have been S-38's triumphant static fire test. The Orbital launch mount's chopsticks moved into position, the ship quick disconnect arms sealed against Starship's hull. Every system appeared ready for ignition, but experienced SpaceX watchers knew something was terribly wrong within the first 10 minutes. The missing piece? Frost formation on S-38's tanks. When cryogenic methane at minus 297 degrees Fahrenheit and liquid oxygen at minus 183 degrees Fahrenheit flow into Starship's fuel tanks, they create unmistakable frost patterns along the vehicle's metallic skin. This visual confirmation tells engineers that propellants are aboard and engines are ready to fire. S-38's tanks remained completely dry. No frost, no fuel, no hope for ignition. The venting that followed told the real story. Initial bursts indicated pumps were attempting to pressurize fuel lines. When that failed, a second wave of venting showed engineers cycling the system, desperately searching for the blockage. By 8:30 a.m., heavy side venting from the orbital launch mount confirmed the inevitable. Fuel was being drained back to storage tanks. The test was officially scrubbed, but the implications were just beginning. This failure reveals the incredible complexity hidden beneath SpaceX's seemingly routine operations. The fuel delivery system at Starbase isn't just pipes and pumps. It's a precisely calibrated network operating under conditions that would destroy most industrial equipment. The process begins at massive storage tanks holding thousands of gallons of supercooled propellants. High-pressure pumps force these fluids through insulated lines stretching across the facility. Temperature sensors, pressure gauges, and flow meters monitor every step of the transfer process. Here's what makes this system so fragile. Cryogenic propellants create challenges that don't exist in normal industrial applications. Microscopic ice crystals can accumulate at connection points. Thermal cycling causes metal components to expand and contract repeatedly. Seals and gaskets face temperature swings of over 400 degrees Fahrenheit. The aggressive testing schedule has pushed these systems beyond their design limits. Between March and September 2024, SpaceX conducted 23 major ground tests at the orbital launch mount. Industry standards recommend comprehensive inspections every 15 to 20 pressure cycles. SpaceX has been operating on borrowed time. Each transition from booster testing to ship operations adds another layer of risk. Engineers must physically reconfigure fuel line connections, swap interface hardware, and recalibrate pressure systems. Every change creates potential failure points. Based on the observed symptoms, 3 primary suspects emerged for S-38's fuel system breakdown. Fuel line blockage represents the most likely culprit. After months of intensive testing, debris from thermal cycling could have formed significant obstructions in the main fuel arteries. Even tiny ice crystals, invisible to inspection equipment, can gradually restrict flow until complete blockage occurs. Pump system malfunction offers another explanation. The high-pressure pumps responsible for propellant transfer operate under immense mechanical stress. Cavitation damage, seal failures, or impeller degradation could prevent adequate pressure buildup. Without sufficient pressure, fuel cannot overcome resistance in the lengthy transfer lines. Interface connection failures present the wildcard scenario. The ship quick disconnect system represents one of SpaceX's most complex mechanical interfaces. This connector must form a perfect seal while handling cryogenic fluids under extreme pressure. Even minor misalignment or seal degradation prevents proper fuel flow. The complete absence of any fuel loading suggests a catastrophic failure rather than a minor leak or partial blockage. This points toward either complete pump failure or total line obstruction. S-38's failure carries consequences that extend far beyond a single test. This vehicle represents the final Starship 5.2 before SpaceX transitions to the revolutionary V3 design. Every day of delay pushes back critical milestones affecting the entire program timeline. Flight 11 was targeting a late September launch window to maintain SpaceX's record-breaking 37-day turnaround between missions. That record isn't just impressive statistics. It demonstrates operational maturity that NASA, commercial customers, and investors monitor closely. Missing the October 3rd deadline would break SpaceX's turnaround record and raise uncomfortable questions about system reliability. More critically, it could force delays in the planned pad renovations needed for V3 operations. The timing pressure creates a dangerous dynamic where engineers face impossible choices between thorough repairs and meeting aggressive schedules. Buried in this technical crisis lies a strategic decision that may have created SpaceX's current problems. Before moving operations to the orbital launch mount, SpaceX conducted ship tests at a dedicated facility called the Massey Test Site. This specialized infrastructure was purpose-built for Starship static fires. Dedicated fuel lines, optimized pumps, and streamlined operations made testing more reliable and predictable. The facility